Hello and welcome to the section 4 of the course Final Project Observing the Dark World. Now in this section we are going to take a look at various points. In this section we are going to learn about prior formulation, we will learn about the construction of loss function, the implementation of PYMC3 and then the final results. So let's start with the first video, choosing priors. Now in this video we are going to take a look at a couple of points. First of all, we will learn about the information of project and then I'll explain you the various components inside it. So first of all, let me show you that what is this project observing the dark world, and I'll also explain you the process to complete this project. So guys, I've started my browser and basically this is the Cagle problem, and you can also check it if you type on Google like observing the dark world Cagle. So this is a Cagle problem and you can find information about this project on that particular website and hit enter. So here you can see the first website, observing dark worlds Cagle, www.cagle.com/c/darkworld. Click and open this website. So here it is. So basically this was the complete challenge here to complete this project. This was the competition. So we need to understand that what is this project, and we need to understand the description of the project here. So this is observing dark worlds. So the question was, can you find the dark matter that dominates our universe? So in our universe there is dark matter. We need to find out the dark matter inside our universe. Winton Capital offers you the chance to unlock the secrets of dark worlds. So this was the price of that project, $20,000, right? Now let me show you the description of this. So let me click on description here, and here it is. So let's read out. So there is more to the universe than the eye. So it means that we cannot see everything in the universe, but there is a lot more inside the universe. Out in the cosmos exists a form of matter that outnumbers the stuff we can see by almost 7 to 1. So the stuff we are watching in the universe, basically we cannot see more than that, right? But in the universe there is a matter available. The matter is called dark matter, and we cannot see dark matter, and we also don't know what it is. What we do now is that it does not emit or absorb light, so we call it dark matter. Absolutely correct, because as we cannot see it, it means that it is not emitting any light, right? That's why we are not able to see that, and that's why it is called dark matter. Such a vast amount of aggregated matter does not go unnoticed. Absolutely correct. In fact, we observe that this stuff aggregates and forms massive structure called dark matter halo. So you can see information here about dark matter halos. So this is a very vast area of dark matter, right? And the massive structures are called dark matter halos. Although dark, it wraps and bends space-time such that any light from a background galaxy which passes close to the dark matter will have its path altered or changed. Absolutely correct. For example, you can see here in the figure here that basically if other galaxies are providing any light here, so the light will not cross the dark matter, and basically it will be altered. It will alter its path, and you can see here that this bending causes the galaxy to appear as an ellipse in the sky. Absolutely correct. So if the galaxy is not ellipse, if it is any other structure, but according to the dark matter problems, according to the altering of path, it looks like that it is elliptical, but it is not. You can see also in the figure here. So this is the figure here, dark matter bending the light from a background galaxy, and in extreme cases the galaxy here is seen as to two arcs surrounding it. So NASA has provided this picture here to explain about the altering of path due to dark matter. Since there are many galaxies behind a dark matter halo, their shape will be correlate with this position. You can see here. At distant circular galaxies are here. This is the A figure. You can see here that distant circular galaxies or dots in this case are randomly distributed in the sky. Absolutely, there are billions of galaxies are there in sky and they are randomly distributed there. Each galaxy has an x and y coordinate. So we already know that each structure has x and y coordinate corresponding to the position in the sky from 0, 40 to 100. Alright. B is by placing a dark matter. So if dark matter is available there, so that the galaxies will not look like a dot. It will look like the elliptical structure. So dark matter halo is middle in the sky between us, and the background galaxies, they are altered such that they become elliptical. That's right. You can see here. However, unfortunately, galaxies are not circular, and in fact, they are inherently elliptical. Alright, this is another case. This property is random, and however, since the universe has no preferred elliptically, this averages out to 0 in the case of no other influence. D case. Therefore, if place a dark matter halo in the field of randomly elliptical galaxies, so if we place dark matter in the field of elliptical, the galaxies are already elliptical, and now we are putting the dark matter in the middle of that. So we would get a field that does not average out to 0 if we can use the fact that dark matter makes the pattern seen in B here. We should be able to detect the position of the central halo. So this is the complete project information here. These are the cases available here, and this is the basic information if you have no idea what is dark matter, right? Now what is the problem? If we talk about what is problem. So detecting these dark matter halos is hard, absolutely, but possible using the data. So if we have the data, if we have done some experiments, so we can gather information about dark matter. If we can accurately estimate the position of these halos, we can then understand the function they play in the universe. Absolutely correct. Basically, now you know that what is halos. Halos are basically the massive structure of dark matter. There are various methods to attack the problem. We have given you some examples already. However, we have not been able to reach the level of precision required to understand exactly what the dark matter is for all dark matter halos, because still we have not enough data to understand exact information about the dark matter. We challenge you to detect the most elusive, mysterious, and yet most abundant matter in all existence. So this is the challenge of this project, right? That's why it is called observing the dark world. So this is the figure number 3, dark matter in action. If you look closely at the real world example, this is real world picture. You can see the wrapped and elliptical galaxies are available here. You can see here that some are dots, some are elliptical, some are circular, and the dark matter is also available there. And these are the challenge organizers here available. Alright, if we talk about evaluation here, so the challenge is to predict the centers or x and y coordinates of the dark matter halos in the test set of 120 skies. So we have 120 skies, and we need to find out the x and y coordinate of the center of the dark matter halos. Dark matter halos means the big massive structure of dark matter, and we need to find out the centers of those dark matter halos. What we are gathering here and what's provided, so we have provided dark matter words metric.python file that you can use to calculate the metric of your estimates of the training data. Alright, all you need are the Python packages numpy, math. So basically this is all about pymc3. We already have that. You know, we have Anaconda, and using in Anaconda we can start the Jupyter notebook, and inside Jupyter notebook we can use pymc3 because we have already installed it. So next is Python dark worlds metric.py. This is information about the files. In order to test your algorithm for accuracy and precision, there will be two parts of the metric. The first part will be how close you get to the true position of the halo. Alright, and second will be to make sure that there is no preferred direction of your estimates. Positions bias. This is the question here. M equal to f divided by 1000 plus g, where f will be the average radial distance from the user estimate to the true position of the halo. So this is a distance, f will be the distance. In the case of more than one halo, we will match up your estimates to true estimates in the configuration that gives the best average radial distance. Okay, what is g? G is calculated by firstly finding the angle of the predicted position with respect to the center of true halo position, where the angle is measured from the estimated position to the line connecting to the true halo position and given reference point. So we will have the reference point, and according to that reference point we can simply get information about the angle. So G is the angle and F is the distance. Okay, you can see this is the formula of G. In the root you can see information about the, so this is the structure here, hello 1 and hello 2, right? This is the radial distance here, this is the radial distance, and this is the theta. Basically this is the angle, right? For example, if we are watching from here, so if this is the center, so this is the complete angle. Okay, this is G and this is F. Okay, we will estimate the vector or distribution of phi over all the halos in the simulation. So there are billions of halos. The reference point is provided in the training halos.csv file for you to evaluate your predictions locally. So this is information about what we are gathering here, what is provided. So there are various files are provided here, various Python files are there. We have the equation here, and we have information about the distance, the angle here, right? So this is evaluation of the observing the dark world project. Now if we check the submission instructions here, so instructions are available here. The challenge is to predict the center of each dark matter hello in the provided 120 test skies. All right, so we need to find out the center of each and every dark matter. Each test sky can have either 1, 2, 3 dark matter halos X and Y. So for example, if there are 120 test skies, so maximum 360 dark matters are available inside it. We are assuming it in this project. Each row of the submission file must have 7 columns in comma separated values. Sky ID, X hello, Y hello, X hello, Y hello, right? For example, there are 3 dark matters in every test sky. So you can see X and Y, 3 pairs are available here, and this is the sky ID, for example, number 1. Similarly, for example, if the sky for which you are making a prediction has fewer than 3 hellos, simply use 0000 as the prediction. Okay. For example, you can see here that there are only 2 dark matters are available. The third one is 00, and this is the one pair, this is the second pair, and this is the number of sky. So there are 120 sky, so this is number of sky, 73 sky number. All right, so this is the basic information about observing dark worlds project, right? And we have given some files, we have given information, we have given the data here that you only have 120 test skies and you can have maximum 3 dark matters. If you don't have, then you can simply put 00 and you can use this information for the project. So this is a very important project, and this was the competition, right? And the prize was $20,000. So this is the data information available here. We check the training data available here, which we have already. No discussions are available here. Leaderboard, who won it, and rules are also available here. So the whole information is available here. You can also check it if you open the website www.cagle.com/c/darkworlds. So this is the basic information about the project.